Okay, so let us resume. So today what we are going to do is go deeper into the study of eigenvalues, eigenvectors. So last time, this is where we ended. We said that we want to, well, we first defined eigenvalue, eigenvector, eigenspace, and then we said that I want to compute these things. And in general, it's not that easy. Maybe in general meaning when the vector space is infinite dimensional, but when the vector space is finite dimensional, then it is indeed the way to do it is basically you take this determinant where lambda is a scalar, replace the lambda by a variable x, and then you just compute the determinant of lambda identity minus a or a minus lambda identity. That should be equal to 0 because this is a matrix in the finite dimensional vector space case. So this matrix fails to be 1 to 1 if and only if it fails to be onto, if and only if it fails to be invertible, if and only if its determinant is 0. So you just calculate this thing. It turns out to be a polynomial, and then work this out for every line, right? So like work this out. You get a polynomial, and you find all the roots that lie in the field, and then those are precisely the eigenvalues. For those eigenvalues, this kernel is the eigenspace, and that is how you compute. So we actually did an example last time, and that is what happens. Now, in general, that's what you do. So let me start now by giving this polynomial a name. And this polynomial will show up several times now. Of course, it is central to doing eigenvalues, so it will show up several times there. But it also shows up in something called the Cayley-Hamilton theorem. Okay, so definition. Okay, so for a matrix T, for a matrix A in F to the n cross n. Okay, and I can do the same as linear transformation as well. Maybe I'll do it later. The characteristic polynomial is exactly this. We give it a name. So it's P subscript A polynomial of A of x is equal, defined to be the determinant of x times identity. If this is n cross n, then n, obviously. That's the characteristic polynomial of x. And as I said, the roots of this polynomial in F are the eigenvalues. Let me just mention that now. The roots in F of this polynomial are the eigenvalues of A. Okay, this is very bad. Okay, fine. So we already saw this one. Let's do examples. One example was here. So let's do examples maybe 2 and 3 or something. Where is that? Let's say A is an upper triangle. Right? Let's call this lambda 1, lambda n, zeros here, and then whatever. Okay. In particular, for example, A can also be, of course, a diagonal. Okay, so it's upper triangular. In particular, the entries above the diagonal can also be 0. So it can also be diagonal. Then what is the characteristic polynomial? Then PA of P PA of X, so let me change P and Y, is determinant X identity minus A, right? That is the polynomial. This is the, let me just write this down. What is X identity minus A? It is X minus lambda 1, X minus lambda 2, X minus lambda n, whatever. Let's say minus star, if this was star, then it's minus star, minus of 0 is 0. So it is still an upper triangular matrix. And if it is upper triangular, we know that the determinant equals the product of the diagonal entries. That was, I guess, a midterm or a homework from the homework 8. Anyway, so which is this literally is product of the diagonal entry, X minus lambda I goes from 1 to n. And so, yeah, so therefore the eigenvalues are exactly lambda 1, lambda 2, lambda. Lambda 1, lambda 2, lambda n by this remark. Okay, great. Now we come to now I need two more definitions. So this is okay. These are all sort of basic results. Now let's get to something called algebraic multiplicity and geometric multiplicity, which we will see again later in this talk. But first, right now, I want to talk about conjugates. Yeah, well, let's do it. So let's see. So definition, two definitions. Okay. One, we say that two matrices are conjugate if one, you can write one as P times B times P inverse. Okay. We say two matrices of the same size over the same field, A and B in F to the n cross n are conjugate okay, if A equals P, B P inverse for some invertible matrix P. Obviously invertible. That is the first definition. And the second one is a two-part definition. So maybe I should just say two more definitions. So the algebraic multiplicity and the geometric multiplicity of an eigenvalue. So given a matrix and lambda a scalar. Okay, so basically there are two different things you can talk about. Given lambda, think about lambda as an eigenvalue of the matrix. Then there are two different things you can talk about, two different numbers you get, integers. One is how many times does lambda occur as an eigenvalue. So for example here, I have lambda 1, lambda 2, lambda n, but I never said they were distinct scalars. They are some scalars. So for example, for the identity matrix, it is x minus 1, x minus 1, x minus 1. They are all the same scalar. Okay. So you can ask how many times does lambda occur among this list? That is the number of roots of this characteristic polynomial which are equal to lambda. That is called the algebraic multiplicity. Polynomials are algebraic objects, and so algebraic multiplicity. The algebraic multiplicity of lambda, let's say in A, is I'll call it AM A of lambda. And sometimes I'll just skip the A, maybe, is to be defined to be the number of roots of PA of X that equal lambda. Okay, the number of roots of the characteristic polynomial that we just defined, determinant of X identity minus lambda, that are equal to lambda. Just a couple of changes here. Algebraic multiplicity. Okay, that is one. And then the other number you can define is, well, what is the dimension of the eigenspace, right? So you have, suppose it's an eigenvalue, then there are eigenvectors, there's an entire eigenspace. What is its dimension? That is called, well, because it's like, what is the eigenspace itself is a vector space. Over real numbers, it's like, you can draw things, lines and planes in it, you can do angles. This geometry. So that's called the geometric multiplicity of lambda. The geometric let's call it GM of lambda. That is defined literally to just be the dimension of V lambda. That is the dimension of the kernel of lambda identity minus A. Okay, so these are the algebraic and geometric multiplicities. It is interesting that the names, the acronyms are still AM and GM, because you might have seen something called the arithmetic mean and the geometric mean of two positive numbers, let's say. And then you have an inequality which says that the AM is always bigger equals the GM. A plus B over 2 is bigger equals square root AB, because it's just a quadratic calculation, completing the squares. Well, it turns out that in this case also AM is bigger equals GM. So there's an AM-GM inequality not just for positive real numbers, but also for linear algebra. And we will hopefully get to that today. So, but now, for now, let me just tell you prove one basic fact about these things. I said conjugate, I said AM and GM. So the point is, if two matrices are conjugate, they have the same characteristic polynomial, the same AM and the same GM. So this is against the proposition. Say AB are so AB in F to the n cross n are conjugate, then AB have the same, I'll call it CAD polynomial, the M and GM for all lambda in M. That is the theorem. That is the proposition. Okay, 1 second. I need to write the homework problem down. Okay. So proof. The proof is not hard. At least the proof of CAD and AM is just straightforward, trivial, right? So maybe we even saw the proof for characteristic polynomial earlier. So say A equals PDP inverse. Then you can just write this down. So PA of X equals determinant X identity minus P P P inverse, because A is PDP inverse, and then this is literally just determinant of P X identity minus B P inverse. That is because P times identity times P inverse is identity, and P times B times P inverse is this. And now you just, like now the determinant is multiplicative, so it will multiply. So, of course, here x is a variable. So I've never told you how to do this over variables. But if you want, so you can do it in two different ways. Those of you who are taking algebra 1, you can work over the ring, which is, you can work over the field. So you can either work over the field in rational functions in one way. In that case, x is an element of the field, and although this is a matrix in the field, fx, and therefore we never said that you can't work over that field instead of just the field f. So in that field, the determinant is multiplicative when you're done. Okay, that is one way. The other way is to say, well, I just want to care about, oh, no, okay, to say that the characteristic polynomials are the same, you actually have to work with the same field. To say that the algebraic multiplicities are the same, you can substitute lambda for x and see if it's 0 how many times, or actually even that may not be the same. The set of eigenvalues you can recover, but to prove algebraic multiplicities, you need to work over this thing. So yeah, so this is not just for algebra 1 people. So let me put a star here, and then I'll justify the star in a second. But this determinant is multiplicative as long as the entries of my matrix belong to my ground field. And we already know that by the main theorem of determinants, the first corollary was that the determinants of inverse matrices are reciprocals of each other, and so you get P of x. And now to justify the star, let me go. Let's first of all break this up into three parts. A for the characteristic polynomial, B for the algebraic multiplicities, and C is the most non-trivial, so we will get to that later, for the geometric multiplicity. But now let us justify the star. So the point really here is that x is an indeterminate. So this equation because we are saying that these are equal as polynomials. We are not saying that they're equal at some value, lambda. So x actually is a variable, it's indeterminate, which means that what we are really doing is, so if you look at x times identity minus a, b, whatever, for instance, this is not in f to the n cross n. So how do you talk about the determinant and that the determinant is multiplicative? Well, it's very simple. What I just told you, you embed this field into a bigger field in which this matrix entries sit. And once you have that, then you can then again over any field, it is the determinant exists and it's multiplicative. So over the bigger field it does, and so instead we embed over the larger field. This is the field of rational functions in x in one variable. Max over f. And what is rational function? It's just like rational numbers. You take a polynomial, instead of saying integer over integer, you say polynomial over polynomial. This is defined to be the set of all px over qx, like p over q, where p and q are now not integers but polynomials. So square brackets means polynomials, round bracket means ratios of polynomials, and of course qx is not equal to 0. Okay, so once you work over this, because polynomials are not closed under division, so they cannot form a field. But the rational functions actually do form a field, verify this form a field. This is a field for all f. So no matter what field you start with, the rational functions over it do form a field. In fact, the rational functions in several variables also form a field, not just in one variable, but we only need it for one variable. Okay, so now what we have is that this determinant, this matrix itself, xid minus b or xid minus this thing, all these matrices lie in not f to the n cross n, but x to the n cross n. Now, xid minus a and xid minus b Okay, these lie in fx to the n cross n, on which the determinant is multiplicative as well. So the debt function now takes fx to the n cross n, calculates the determinant, and gives you a scalar in that field. The scalar in that field is the rational functions. Is once again multiplicative. Yes. And that is what justifies going from this product of three matrices determinant to the product of the three determinants themselves. This explains, justifies. Okay, so that's the reason for putting this stuff. And then once you know this reason, then of course, the fact that the two characteristic polynomials are equal is trivial. The only thing is you have to make sense of this step, and that's what we are doing. It is that you don't work over the field F, you work over the field F at joint ends. Okay, great. So now, simplifying. Okay, great. So that is one thing. Now, if you know that the characteristic polynomials are the same, then well, you know all the set of roots and their multiplicities are the same. So that directly, if the polynomial is x minus 1 to the n in both cases, then 1 of course is an eigenvalue with n multiplicity. So AM is this trivial. Sorry, this AMD of lambda. Trivial from trivial or immediate. Okay, and the property C is the real tricky part, so let's get there. The geometric multiplicity, if two matrices are conjugate, then their geometric multiplicities have to be. Okay, so why is that? No. Okay. We have started it. Okay, so now let's see. So geometric multiplicity is the same. Okay, so let's take to fix a scalar lambda, and let's look at the eigenspaces. Geometric multiplicity. Okay. To check, actually, I should have said check it as a fixed lambda. And let's call this, let's say, b lambda a and b lambda b. And these are, since b is fn, let's say b fn, denote the lambda eigenspaces or E spaces, as the same time it keeps calling them now, lambda E spaces of a comma b respectively. We want to show that the dimensions are equal. Okay. So we first claim the following. First claim for any vector in f to the n that bv equals lambda v if and only if a times pv equals lambda times p. And that is pretty trivial. Why is it trivial? Because a times pv equals lambda pv if and only if p inverse ap of v equals lambda V. But P inverse AP is precisely V because A equals PDP inverse. Okay. And similarly, A, let's call it V prime, equals lambda V prime if and only if B times P inverse V prime equals lambda times P inverse V prime. Okay? V or V prime or whatever. For any V in V and V. So as a result, what I'm saying is the following. Okay? So what this says is that if you look at the maps, if you take the lambda, let's say V lambda B and V lambda A, you look at these two vector subspaces of vector n, then there is a map. If from taking, so this is a vector in this space, PV is a vector in this space. So if you do P times whatever, then that map takes eigenvectors here to eigenvectors here. And moreover, this matrix is invertible, so this transformation is invertible. We've already seen that. And similarly, there's a reverse map exactly by the second line, which is to multiply by P inverse. So you get two vector spaces, but you also get two linear maps. And what if you compose them either way? Well, you start with the vector, then you multiply by P, then you multiply by P inverse. But then that means you're just multiplying by the identity, so you get it back here. Similarly, you start with the vector here, you multiply by P inverse, and then you pre-multiply by P. So again, you're just pre-multiplying by the identity, so you get back to the same vector. So you have two linear maps. Pre-multiplication by a matrix is a linear map. We all know that. You have two linear maps between two vector spaces, both of which compose to the identity map. And that is enough to prove that the vector spaces are isomorphic. In fact, that's part of the category theory definition or something. Provide linear maps between VA and VB, VA lambda and VB lambda, such that the compositions in both directions are identical, which compose in both ways to the identity maps. To identity maps, and therefore it's hence they are isomorphic. I mean, so these maps are actual isomorphisms, not just maps. These things are isomorphic in the category of vector spaces, which means these maps are linear isomorphisms, so the dimensions are different. Okay, great. So that is what it is. So that's the GM equals GM. That is the end of the proof of the proposition. That if you have two matrices which are conjugate, then the algebraic, the characteristic polynomials are equal. That required working over a slightly larger field of rational functions. Therefore, their algebraic multiplicities are trivially equal. The geometric ones are also equal for a very simple reason. You have actual linear isomorphisms between the eigenspaces themselves. And instead of telling you that the eigenspaces are the same dimension, I'm actually providing for you linear isomorphisms between them. So of course they are the same dimension. That's the proof. Okay, what next? One homework I've already given you. And that I've already given you in homework 9, I think. Yeah. Okay, so now let's talk about. So what else can you say about the eigenvalues? Right? So eigenvectors. So if you have eigenvalues which are distinct, actually you have seen this in some sense in UM 102. not some sense. It's sort of morally somewhat similar, not in any way precise. If you have orthogonal vectors in a inner product space like Rn or whatever else, then you can then you know that orthogonal vectors are linearly independent. Well, something similar happens for any vector space or any field. If you have eigenvectors for different eigenvalues, then they are linearly independent. This is actually very useful when in sort of higher algebra and so on. So when you have something like what one calls a semi-simple Lie algebra, and you look at some theorems about that, you can break things down into a sum of eigenvectors uniquely corresponding to distinct eigenvalues because they are linearly independent. So let me just mention the proposition now. Let's call it proposition 2 because the previous one was proposition 1. Let's say. Okay. Again, the usual thing. So, okay, so say V. This time I won't ask for finite dimensionality. Say V is a vector space over F, and T is a linear map from V to V, and let's say lambda 1 and lambda n are the same. Distinct. So these are n distinct scalars. Okay, so now 1. If you have non-zero vectors in each eigenspace, if 0 V not equals Vi belongs to V lambda I for all I, then these vectors Vi are linearly independent. Let's say V1, V2, Vn. Okay, they're linearly independent. That's very nice. Okay, great. And the next thing is, what was the next thing? In particular, the sum of these eigenspaces is direct. So maybe that's the third. Third point. By the way, over here I told you that the geometric multiplicity of every lambda is equal for A and B. That can also be true if lambda is not an eigenvalue. So in that case, these two will both be 0. Okay, so when lambda is not an eigenvalue, the eigenspace is 0 because the kernel is because the transformation is 1 to 1, so the kernel is 0. But even then both sides are 0, so that's fine. And similarly here, the sum of the eigenspaces, I'm not saying that these are eigenvalues. So this, but here I'm assuming that suppose this is an eigenvalue and this is a non-zero eigenvector. In this part, I am not assuming that. The sum of the eigenspaces V lambda 1, V lambda 2, V lambda n, which may be 0, is direct. In other words, if you look at the summation map, then that's that's isomorphism. i.e., if you look at the map from take the Cartesian product of these V lambda i's. On the other hand, I'm saying this is a direct sum. But the point is when it's a finite Cartesian product, you know that this is also equal to the finite direct sum. So indeed it's a direct sum. Okay. To V, this map sending, let's say I don't know, V prime 1, V prime n, to summation V prime I, is an isomorphism, is a linear isomorphism. Sorry. It's not an isomorphism. I'm not saying it is onto. It is just it's 1 to 1. It's a linear, it's of course linear. I'll just say it's 1 to 1. This is part 2. And part 3 is an obvious consequence. If you have, suppose my vector space was finite dimensional, or at least all these vector spaces were finite dimensional, then if you look at the direct sum inside V, then the dimension equals the sum of the dimension. So what is this what is the image of this map? You have to say that. Remember, we have defined this, right? This is the least upper bound of the vector spaces B lambda 1, B lambda 2, B lambda n. It is the Minkowski sum. It is the set of all vectors which are sums of finite sums of elements, one from each of the subspaces in question. In this case, there are only finitely many subspaces, so there are only finitely many elements. Where is the pen? So it's an isomorph. So this map from the direct sum to the sum, or the direct product to the sum, is an isomorph. So that's what this part 2 is saying, and therefore, in particular, regardless of if V has finite dimension, if all the VI's are finite dimensional, V lambda is. Oops. This is not lambda, this is V lambda I. Then what? Then the dimension of the Minkowski sum equals the summation of the sum of the dimensions. Okay, great. So that is what it is. Fine. These are what we okay. Let's start. So let's prove these things. Let me take a break from this pen, just to not tax it too much. So this is where I'm going to use the homework problem I gave you in homework 9. There is something called the Van der Waals matrix. Okay. Great. Okay. And so suppose I have a linear combination of these guys. Suppose these VI's are independent. So suppose summation Ci Bi equals 0. Well, this is the same as saying, well, this is like this. If I take now, I'm going to apply T to this linear combination again and again. Okay, so this one is like this T raised to 0, because T raised to 0 is the same as doing nothing. The identity implies T raised to 1, T raised to 2. Okay, all of those are 0. So let me just say 0 equals this thing. 0 thing. And so if I apply T raised to j on both sides, T raised to j of any 0 vector or any linear map is linear. But now what is this? Because it's linear, I can take Ci T raised to j of Vi. And this was your homework problem. If V is an eigenvector, then T has eigenvalue lambda I, then T raised to j has lambda I power j. So this is literally Ci lambda I power j Vi. Sorry, not 0 to n, I is 1 to n. And this is equal, these things, so 0 equals this combination. Let me just take the first n of those powers for j equals 0, 1 till n minus 1. Okay, so let's write this down. Let me now show you what happens for 2 by 2. Okay, so I get C1, so easy for n equals 2. C1 V1 plus C2 V2 equals 0, and C1, or let's Okay. And then what I'm going to do is I'll take the C1 V1 inside and the lambda outside. So let me, if I do that here itself, Ci Vi. Okay. And now say lambda 1 C1 V1 plus lambda 2 C2 V2 equals 0. Okay. Great. So now what do I do? I can write this down now as a matrix. I'll write this down as C1 V1. It's a bit strange that I'm writing down vectors in a vector space as entries of a matrix. I'm just expressing this in compact notation. Okay? This is the same as saying if and only if. So C1 V1 plus C2. So 1 times C1 V1 plus 1 times C2 V2 is 0. And lambda 1 times C1 V1 plus lambda 2 times C2 V2 is 0. Okay? But now look at this matrix. This is called a Van der Waals matrix, and this was in homework 9. So this was there in the homework 9 section. And you know from there that if the lambda is a distinct scalars, look at the formula of the determinant of that matrix. You actually are asked to compute that, and it was actually a non-zero quantity if the lambdas are distinct. In particular, this matrix is invertible. So if I call this matrix P, then I can pre-multiply by P inverse, which just means that I can take some linear combinations of these two equations. And you know that pre-multiplying is amounting to doing some row operations. So I can take linear combinations of these equations, and I would just be able to get back that this and this is identity. On the other hand, pre-multiplying this by 0 and 0 gives you 0. So I get identity times C1 V1 C2 V2 equals 0 0. So C1 equals 0, C1 V1 is 0 and C2 V2 is 0. And that's the exact same thing that happens in any dimension. The moment I multiply by all these different powers, what I get is the entire Van der Waals n cross n matrix times C1 V1 C2 V2 CI equals 0 0 0. Pre-multiply by P inverse, I get each Ci Vi equals 0, and then therefore Ci must be 0 because Vi are non-zero. Okay, so let's write this down. This is n equals 2. More generally, the same thing happens. More generally, space. We have the same equation. I'll just write the same equation down. There's nothing different here. 1, 1, 1, lambda 1, lambda 2, lambda n, lambda 1 to the n minus 1, lambda 2 to the n minus 1, lambda n to the n minus 1. C1 V1 Cn Vn equals 0 0 0. So this should be C2 V2 as well. Okay, so more generally that is what happens. That we have this whole matrix times C1 V1 C2 V2 equals 0. But now let's call that matrix P, pre-multiply by P inverse, and by homework 9, that P is non-zero because the lambda is a pairwise distinct. We know that. Okay? Because I know that the lambda is a distinct, by assumption that P is non-zero. So P is invertible. So I can therefore pre-multiply P inverse times P times C1 V1 Cn Vn is P inverse times 0 0 which is just 0, of course. So I get a system of equations, I take some more linear combinations of that system, and I get 0, 0, 0. Okay, and therefore, but now we are done. This is identity, and therefore I get the CI here. Why does that imply that each, so now I won't write this down, but why does that imply that each of the CI is 0? So CI is 0. I should just say 0 here for all I. The claim is because Vi is non-zero, this implies Ci is 0. Why? What happens if Ci is non-zero? Well, I'll leave it to you to think about, right? But this is, I'm just going to say this is obvious. And remember, what we started out was by saying, suppose linear combination is 0. We conclude by saying that the coefficients must be 0. Therefore, the vectors Vi are linearly independent. Okay, so that is part A. Now let's go to part B and C. Oh, sorry, that's part 1. Oops, I forgot to write part 1. Now let's go to parts 2 and 3. The second part is just the part that it's a direct sum. Actually, is there anything to say there? So part 3 is obvious from 2. So I won't even do part 2 and 3. Work it out. Part 3 is now obvious. So for this you don't even need to work it out, right? If the vector spaces are whatever, then the dimensions are the same. This is obvious. We need it from 2. Okay, so I won't do those. You can work it out. Now that's it. Now we come to diagonalizable maps, and hold on. I never remember what time it started. Okay. About 40 minutes left. Okay. Okay. So, diagonalizable. But basically, part 2 is just obvious, right? If you are saying that this is 1-to-1, the summation map from the direct sum or the direct product to the Minkowski sum is 1-to-1. Well, take a look. Suppose you have V1, V2, Vn, and you add them up and it goes to 0. Then that's a linear combination which is 0, but that cannot happen. Right? So that's all. Oh, sorry. That can happen. The only way that can happen is all of those VIs must be 0, 0, 0. So here's a linear map from the Cartesian product to the Minkowski sum, whose kernel is precisely the origin, 0, 0, 0. That's exactly a 1-to-1. That's all that part 2 was saying. So it's literally exactly from the thing. So basically, if the sum of these things is 0, then it violates part 1 unless all the VIs are equal to 0. So the assumption that in part 1 that was there was all the VIs are non-zero. That assumption must fail. And so you have to do this like whatever. You have to do this for induction, number of things, number of smaller things or something. No, you just okay. Maybe I'll write this down. Fine. It's basically trivial, but one has to say it a little carefully. So let me say it a little. Part 2. Say phi from product V lambda I to V sends or to V or to summation V lambda I sends V1 V prime 1 V prime n to summation Vi prime I. Okay, and phi of V prime 1. Let phi takes the elements of phi are elements of this. The domain of phi is the set of all tuples because it's a direct product. So the elements of this is 0. Okay. The claim is that each of those VI's is V prime i's is 0. Okay. So suppose not. Suppose there is at least one. So let's say I subset of 1 through n denote or not denote comprise, I guess, consist of comprise suppose there is at least one. Okay? The claim is that this is non-empty. The claim is that this should be empty. So all of them should be 0. If I is non-empty, then what do we get? We get that the sum of all those guys we have now not I goes from 1 to n, but I in I, v prime I equals 0. But this is a linear combination. 1 times v prime I. So how can we get 0? Because remember, these guys are in v lambda I. These are pairwise distinct eigenvalues, and so they are linearly independent. And this contradicts. Now we are saying all of these terms are non-zero vectors. There is a linear combination that is 0, but they were supposed to be linearly independent. So how can that happen unless the sum is an empty sum? If the sum is non-empty, the non-emptiness would contradict RK. Implies I is empty and we're done. What was I? I was a set of vectors which are non-zero in the eigenspace. But then I is empty means that all of the VI's must be 0. But what was this saying? We started by assuming that phi of this vector is 0 and concluded that all of these coordinates are 0. So so the kernel is 0, therefore phi is 1. Is 0 in where? Is 0 in this space. And phi is linear, so phi is 1. That was the proof. Part 3, as I said, leave it to you guys to check. I think we may even have done this before, that if you have a direct sum of vector spaces, then the dimensions add, or finite dimensional vector spaces, then the dimensions add up because you can take basis and basis and really. Oh, sorry. You work this out, so let me say that. I such that v prime I is non-zero if I is non-empty. Okay, now we started diagonalizable maps. Actually, do I want to do AMGM first or second? What is going on? I want to do AMGM for diagonalizable right now. That's why AMGM comes next. Okay, fine. So let's start with diagonalizable maps. Okay, we should be able to do. Yeah. Okay, so remember that the matrix is diagonal. Recall or maybe note, if I didn't say before, a matrix A or actually B, let's say. Here is a different way to define a diagonal matrix. It is that the standard basis is a basis of eigenvectors. Okay, because well, obviously the EI, so if you have lambda 1, lambda 2, lambda n as a diagonal matrix, then lambda, this matrix times EI is lambda I times EI. Okay, and it's if and only if, because the standard basis of f to the n is an eigenbasis, meaning consists of all vectors are eigenvectors. Let's call this A n cross n. Maybe I'll just is an eigenbasis for A, i.e. IEEI is an E vector for all I. One way is obvious, actually both ways are obvious. If A is diagonal, lambda 1, lambda 2, lambda n, then A times EI is lambda I times EI. Conversely, if A times EI is lambda I times EI, check for yourself, I won't even ask you. At this point, this is sort of trivial stuff. Check for yourself that A must be the diagonal matrix lambda 1, lambda 2, lambda n. Okay, so well, basically A is the diagonal matrix whose ith entry is the eigenvalue for EI. That's a diagonal matrix. So now, in exact correspondence, a diagonalizable matrix is one that has an eigenbasis. It need not be the standard basis, it can be some other basis, but there exists a basis of eigenvectors for A. That is a diagonalizable matrix. That is one way to say it, and then I will immediately write down the lemma, or maybe in a minute, in 2 minutes, which says that which gives you a different only if characterization of a diagonalizable matrix, which is the characterization, which is the form that we saw actually last class already. We opened the chapter with that form, this chapter. So the definition, A belongs to F n cross n is diagonalizable if there exists an eigenbasis for it. Or if it has an eigenbasis. Okay, that's the definition. Okay. So the theorem or the lemma or whatever is A is diagonalizable henceforth I will stop saying diagonalizable, I will say diag apostrophe BLE. Okay? If and only if there exists a diagonal matrix B D in F to the n, so this is again n cross n obviously, and an invertible matrix P. Again F to the n cross n, at which point you might start to think, okay, wait, I have seen B and P and A in an equation before. That is exactly this equation, such that A equals P times D times P inverse. And because A is conjugate to D, you know that the eigenvalues of A are going to be the eigenvalues, the diagonal entries of D, and the arithmetic and geometric multiplicities agree and all that stuff. Okay, great. So now we have so let's prove this. I mean, the proof is basically the same thing as what you have already seen last time. All those VIs are the columns of P and so on. So, okay, that's it. If you're going to prove it, let's see. Let's start with A is diagonalizable, then there exists a basis. Say A VI equals lambda I VI for 1 less equals I less equals N. So remember, this is of F to the N. So the basis must have size N. So that's the basis. With, I'll just say V1, V2, with and VI are linearly independent. Ideal basis. Right? If you have a linearly independent set of size N in F to the N, then it's a basis. We already proved that. So I'm not saying the lambda i's are distinct scalars, they're just some scalars. Then let P equals the matrix with these columns. And check, and D equals, of course, the matrix with these diagonal entries. And check that A equals PDP inverse. What do I check? I want to check this. Let's see. Let's look at P dP inverse of V1 Vn. Okay? So I'm just going to look at this column by column. So so that is first of all, let's do it the correct way. I'll do that. I'm exactly going to do that, but let me say it differently. This is a column vector. This is a column vector. This is a column vector. So this is actually a matrix which is n cross n. Even though it looks very, very long, it's just n cross n. Okay. Now what am I saying? I'm saying that this is first of all, because you can do matrix whatever. Just like scalars can be taken out of vectors, you can do the same thing here. This is like block matrix calculations. Okay. This is just block matrix calculations. It's true. But now this matrix is P. This is P times D. Now again we write this down. So now it is V1, V2, Vn. This is P, lambda 1, lambda 2, lambda n. This is D. And you can check this is exactly equal to lambda 1 V1, lambda 1 V1, lambda 2 V2, lambda n Vn. Okay? But what was PDP inverse? This was exactly A. Oops. No, we haven't said that. This is equal to lambda. What is lambda IVI? That is AVI. Oops. That's good. This is AV1, AV2, AVN. So column by column, I'm just doing all of the calculations at the same time, but I could just have said one actual vector instead. That would not matter so much. But anyway, column by column, you see that PDP inverse and A both are n by n matrices which act in the same way on a basis. Therefore, they act in the same way on every linear combination of the basis. Therefore, they act the same way on the entire vector space. And therefore, they are the same matrix. Right? I don't know if you have seen, we must have seen this before. If two matrices act on, we saw that before. A equals B if and only if AB equals BB for all V. Yeah, we saw that. So by that calculation, I'll just say that. So it implies PDP inverse of VI equals A VI for all I. So PDP inverse equals A. Recall A equals B if and only if AB equals BB for all B, if and only if on the basis or on the spanning set. For all B in F to the N, or all be in a basis. We have seen this in class already. Long ago, long ago. Two matrices are equal if and only if they act on the same. They act in the same way on the basis or on the entire space. So that is one implication. Conversely, suppose I know A equals PDP inverse. Sorry, again write P with the columns and D with the diagonal entries. And now, of course, I'm going to claim exactly this happens. Let's check. I'll again check it in the same way. It's basically the exact same calculation done in the reverse order. AV1 into Vn, AV1 AV to AVn is now I start instead of the PD I'm doing the A's. Now I take A, V1, Vn. But what was A? A was P times P inverse, and this matrix is P. This is P times D, which is this. Which is V1, Vn, lambda 1, lambda n, and you know what that is. That is equal to lambda IPI. But therefore, AV1 equals lambda V1, AVn equals lambda Vn, and we are done. We are not done. So you have a set of eigenvectors. You need to say they are a basis. But well, the basis is because, moreover, V1, V2, Vn, the same kind of idea, is P. Is P times identity, which is P times E1, E2, En, equals PE1, PEN. Which means that each VI is P times CI. And I think, again, we probably have seen that if you start with the basis and you take an invertible linear transformation, then because the invertible linear transformation is an isomorphism back to Fn, basis goes to basis. That also we have seen. Since P multiplied by whatever from Fn to Fn, because P is invertible, therefore this is a linear isomorphism. Therefore, basis goes to basis, and so the VI is also formed basis. The set of the tuple, maybe the ordered set. Also forms an ordered basis or vector basis. So indeed you have a basis of vectors v1, v2, vn, and each of those vectors is an eigenvector. Therefore you have an eigenbasis and you're okay, good. That's why matrices are diagonalizable if and only if this happens. Okay, fine. isomorphism. Okay. Let's do some examples and then at least I'll write down the AMGM inequality. Maybe I won't prove it and we'll continue next time. Okay. Examples. Examples of diagonalizable maps and of non-diagonalizable maps. There is also one that will be not diagonalizable. Okay, so first of all, obviously, so I already told you PDP inverse is every single diagonalizable map, so that is not an example. But here are some non-trivial examples which you may not have seen. So let's say F equals R. Real. So this is very, very specific to real matrices. Okay, F is R and A equals A transpose. It's symmetric. So every real symmetric matrix in R to the n cross n is diagonalizable. And as I said, from now on, I will just say apostropheable for diagonalizable. There is a name. This is a famous theorem. We will actually see it in the course. This is called the spectrum theorem. In fact, this is true not just for real symmetric matrices, but something called complex Hermitian matrices, where you take the transpose and then the conjugate, and then you get back this matrix. Anyway, we will see this later. This is one. And now this is an example that is not covered by this other theorem, of course. Okay, so now here is another example, which is now not diagonalizable. But of course, proving that is, you cannot use the above theorem to prove it. So you have to figure out a different way to prove diagonalizability, and we'll get to that. Okay? That's where we are getting to. In fact, second, if you look at A equals, let's say 1, 1, 1, 0. And this is not diagonalizable. I should not have written all of this. Fine. How do you show that something is not diagonalizable? You use this. This result. If it were diagonalizable, it should have a basis of eigenvectors. So first, let's calculate the eigenvalues of this. Okay. Yeah. The eigenvalues of this are what? Okay, let me make it slightly more general because it absolutely doesn't matter. Take lambda to be some common scalar, lambda and lambda. Okay. And lambda 0, lambda 1, 0. Okay. So why? So let's prove. I'm actually going to prove this for you. And probably then we can start. Well, as I said, I will state the AMGM inequality and then we will start. So it's not diagonalizable, why not? And so what are the eigenvalues of this? Because it's upper triangular, the eigenvalues are lambda and lambda. Because it is upper triangle. So I should have, if it were diagonalizable, I would have a basis of eigenvectors. Of lambda eigenvectors. But then what does that mean? If I look at A times C1 V1 plus C2 V2, this is C1 A V1 plus C2 A V2, because obviously A is a linear transformation. But A V1 is lambda V1 and A V2 is lambda V2, because these are lambda eigenvectors. So lambda can be taken common. And I can get back the same linear common. A times that is lambda times this for all C1 and C2. Right? I don't need to say all this, sorry. Because of exactly the same calculation. So what does this mean? It means that A times, okay, very interesting. The plastic, yeah. Even better. Great. So this implies A times V1 or A times Vi equals lambda times Vi, or I equals 1 comma 2. I equals 1 comma. So here is a matrix A which acts on a basis by lambda. Now let me give you a different matrix A that acts on the same basis by the same way. Also identity 2 by 2 times bi. Sorry, lambda identity times. Yeah, oops. Let me just say this in the same line. This is also equal to lambda times identity 2 by 2 acting on bi for all. And again from the class, we remember that we have this calculation. If you have two different matrices, if you have two matrices, lambda identity and A, which act on the basis in the same way, then they must be the same matrix. So here are two matrices that act on the eigenbasis in the same way. So they must be the same matrix, but they are clearly not the same matrix because this is not a diagonal matrix. That's a contradiction. Contradiction to what? Contradiction to this. If A is diagonalizable, then this happens. Well, A is not diagonalizable. Implies by class A equals lambda times identity. This is a contradiction. So A is not diagonalizable. A is not. So A is not diagonalizable because that's why. Okay, so that's basically the end of today's class. But let me just remind you of the arithmetic and geometric, sorry, not the arithmetic, the algebraic and geometric multiplicities. So the AMGM inequality now for linear algebra. So I will state the theorem. I'll remind you what AM and GM are. In linear algebra, I'll even put a smiley face. Okay, let's remember what are AM and GM for a specific eigenvalue and a specific matrix. By the way, I keep saying matrix here, but everything is valid for a linear transformation of a finite dimensional vector space because, I mean, with respect to any basis, the eigenvalues and so on are the same. Right? Okay, so recall given A, which is a square matrix over the field, and lambda scalar. So AM A of lambda is number of roots equal to lambda of the characteristic polynomial equal lambda, and GM is the dimension of the eigenspace. Kernel of lambda identity. I'm not saying that lambda is an eigenvalue, I'm just saying that these are what they are. They can be zero. So, proposition, I'll state it for linear transformations, but it's the exact same. So, I thought that's why I said, why don't I give you some result for linear transformations? So, say V is a finite dimensional vector space. F, P is a linear map, and lambda is a scalar. That's exactly the same as the above, but stated for T for a change, just for some variety. Okay, so then either there are exactly two things that can happen. Lambda is not an eigenvalue of T, and AM equals GM equals 0. Or lambda is an eigenvalue of T, and then neither of them is 0. Both of them are bigger equals 1. So first of all, let's say GMT of lambda bigger equals 1, and the algebraic multiplicity of lambda is at least as big as the geometric. Okay. So either lambda is not an eigenvalue, in which case both of these are 0, or lambda is an eigenvalue, and both of these are strictly positive. But in fact, moreover, the algebraic multiplicity exceeds the geometric multiplicity, or rather, it can be no smaller. Okay, so that is what the statement says, and so that is where we are going to go next. Okay, so I think that is enough for today. We will start next time with the A and G inequality, and we will prove it. And then we will get, so then we will use, the point is, I reintroduce the AM and GM, because now we are actually going to use it to understand when a matrix is diagonalizable or not. So sometimes it is, sometimes it isn't. And this will provide actual if and only if for when it is diagonalizable. The AM, not this inequality, but the use of the AM and GM. Okay, basically the AM and GM equality is diagonalizability, and sometimes it's unequal and then it's not diagonalizable. So just like here, you see, the geometric mean, you can take the geometric multiplicity, is 1. There's only one dimensional eigenspace, while the algebraic multiplicity, as we already saw, was 2. So 2 is strictly bigger than 1, this matrix is not diagonalizable. If they were equal for every lambda, then it would be diagonalizable. That is the effect. So the AMGM equality is diagonalizability. But first, let's start with the inequality. Okay, that's it for today.